All right, next up we have Jandrie Rodriguez, who joins us from East Los Angeles College. Jandrie has been working with Alex this summer, and she'll tell us about her project, Chemical Abundances of the Most Metal-Poor Globular Clusters in the Milky Way, ESO280-SC06. All right, go ahead whenever you're ready.
Thank you, Gwen, for that introduction. Good afternoon, everyone. Thank you for joining us today. So as Gwen has said, my project is focusing on globular clusters. So I will start off by explaining what globular clusters are. So globular clusters are compact, gravitationally bound ancient systems that mostly orbit in the galactic halos, and they can hold up to 10 millions of stars. Globular clusters have also been found in almost all galaxies so far, so this is a common system. The system is born within the same molecular cloud, so it was originally thought that they should all have the same chemical abundance through it. But however, all globular clusters that have been studied so far contradict this. So I will explain the chemical abundance abnormality with a specific globular cluster NGC6752, where there's a sample of 20 stars plotted by Bastian and Lardo depicting its amount of nitrogen over iron versus aluminum over iron. And these elements are over iron because iron is the same throughout all the stars, so it's used to normalize the rest of the elements. So the stars are color-coded by black, red, and green. The stars that are color-coded by black show that this should have been the range where all stars would have fallen if they had the same chemical abundance. And the reason for this is that this range is seen within the globular cluster, but also stars surrounding the globular cluster fall into this range as well. And the red and green color-coded stars are stars that have this high abundance that is only seen within the globular cluster. So taking a closer look, stars that are color-coded with the black show that they have a low amount of nitrogen and a low amount of aluminum. And the rest of the stars have a high amount of aluminum and a high amount of nitrogen. So when a star has a high concentration of an element, it is considered enriched. So here we have a sample of 20 stars with 13 of our stars being enriched. So we would say that this globular cluster has an enrichment fraction of 13/20 or 65%. Also, enriched stars are considered multiple populations, but for our project, we just called them weird stars. So the stars that fall into the black dot regions would be considered normal stars. Globular clusters also have a star-enriched trend. So here we have several globular clusters that are being plotted with its mass versus its enrichment. And we have a function that is this red line here showing the trend that globular clusters have. So this trend is that as mass decreases within the globular cluster, the number of enriched stars decrease as well. So in general, what's interesting about globular clusters is that we've seen this abundance abnormality in all globular clusters so far, but there is no explanation to this. So hopefully as more globular clusters begin to be analyzed, the closer we are to knowing why they behave this way. And as a key insight, the majority of globular cluster data at the moment is mainly on luminous and high metallicity globular clusters. So my project is focusing on an extreme case, which is the globular cluster ESO280-SC06. And the reason that it is an extreme case is that it is one of the most metal-poor and least luminous globular clusters in our galaxy. So since this type of globular cluster hasn't been studied as much as other globular clusters, our first question was if it actually had any of these weird stars. And then if it did have any of these weird stars, would it have followed the globular cluster enriched trend? So at the beginning of our project, we predicted that our sample of stars should have 30% enrichment since its solar mass is 10 to the 3.5. We started off our project using 10 stars with high resolution spectra using Mike's spectrograph with Magellan, and we conducted the first chemical abundance analysis on ESO280-SC06 with spectroscopic analysis and photometric stellar parameters. So the spectroscopic abundance analysis was done with the program SMHR, where I measured the line strengths, which is equivalent with, and the stellar parameters, which are effective surface temperature, surface gravity, metallicity, and microturbulence. And with both of these, the program was able to infer each star's element abundance. Afterwards was the photometric stellar parameters, and it was done using the survey Gaia EDR3, where I plotted the 10 stars photometry data on a color magnitude diagram, where color is the x-axis and the y-axis is the magnitude with a distance modulus. I also added an isochrone with an age of 10.5 gigayears and a metallicity of -2.5. I then de-reddened the photometry data to take into account the dust from us to the globular cluster. And this showed that the isochrone was actually the best fit for our data, which was great because that meant that I was able to interpolate the isochrone to then get the effective temperature from the color and the surface gravity from the magnitude with the distance modulus. I then input these two stellar parameters into the program semi-char again to then get the other stellar parameters, which are microturbulence and metallicity for each star. Another part of our methods was to do spectral synthesis on certain elements such as aluminum, nitrogen, and barium. Due to its molecules blend and hyperfine structure, it was incorrect to use equivalent width to determine how much of the element was within the star. And this is an example of a nitrogen enriched star. So the spectrum is the black line, and then the best fit is the orange line. And that was done using chi-squared minimization. I also added a purple line here to show if the star actually had no nitrogen, just to take in context how much nitrogen this star actually has. So once these steps were done, I was able to get my results. So these are the stellar abundances, or a few of them, for ESO280-SC06. I added 3 plots where I have nitrogen versus aluminum, magnesium versus aluminum, and nitrogen versus sodium. And again, they are all over iron because iron is the same throughout all of the stars, so it normalizes the rest of the elements. And as a reminder, the sample we had was 10 stars. So each square is a star, and the error bars depict how well the stellar parameters were and the spectrum noise. If you take a closer look to the plots that contain nitrogen, we have 3 stars that have arrows pointing to the left. And these are upper limits. And the reason that they are upper limits is because there was no nitrogen absorption within the spectrum. So it is very unclear exactly where they will lie on this plot. Afterwards, it was time to find out if we had any weird stars and how many did we actually have. So I used the previously mentioned globular cluster NGC6752 to identify the ranges of where the normal stars would be and the weird stars would be. So the gray shaded regions is where the normal stars would be, and the green shaded region is where the weird stars would be. And none of the upper limits were added because to the nitrogen plot region because since we are unsure exactly where they would lie, they fall out of the range either way, as well as this nitrogen enriched star, which I will get to later. So just focusing on the middle plot, which is magnesium versus aluminum, we see that 3 of our stars fell into the normal star range and 7 of our stars fell into the weird star range. And since these elements have no upper limits, we can confidently say that ESO280-SC06 has 70% enriched stars. So now circling back to this nitrogen enriched star, which is highlighted in yellow, I plotted this star on a nitrogen versus barium plot to show that it's due to mass transfer from an asymptotic giant purge star due to not only its high amount of nitrogen, but also its high amount of barium. So I did not add it to the previously weird or normal ranges because I can't say that it is enriched just because it is in a globular cluster since it has outside factors for it being enriched. And now we answer our second question, if our globular cluster will follow the trend. And as expected, we expected 30%. So we were a bit perplexed when we got 70% enriched stars. So from this, we either thought that the globular cluster trend needed to be improved to take in this outlier, or that if our globular cluster fell into this trend, then it must have been previously more massive. And we actually believe that this is the case as we then started to research its orbit. So I coded its orbit using Gala and Gala-centric coordinates. And here its orbit is the blue line, and I have a legend to show what is the sun, the current position of ESO280-SC06, as well as where the Milky Way disk would be. From its orbit, we found out that its apocenter is 14 kiloparsecs and its pericenter is about 1 kiloparsec. And here is a movie to show its orbit, hopefully. So as seen here, it is actually passing through the Milky Way disk several times. And again, this is just a period of 1 gigayear. And we assume that ESO280-SC06 age is around 10.5 gigayears. So it has been passing through the Milky Way disk several times, and we believe that it's been losing mass due to tidal disruption. We then collaborated with Anna Bonazza to use one of her codes to find the initial mass of the globular cluster. And I provided a 68% confidence interval. So 68% of our time, our globular clusters should have around this range. And Anna Bonazza found out that our globular cluster initial mass was around 10 to the 5.1 solar masses. So it actually aligns pretty well with our confidence interval. And just a few highlights from my project is that the globular clusters have a wide range of chemical abundances, and we don't have an explanation to it yet. We did the first spectral analysis on ESO280-SC06, and from this, we found out that low luminous and low metallicity globular clusters contain wide ranges of chemical abundances, as luminous and high metallicity globular clusters do. And we found out that this globular cluster has 70% enriched stars falling out of the globular cluster trend, but we believe it is due to losing mass from tidal disruption from passing through the Milky Way disk. Thank you very much for listening to my talk today. Does anyone have any questions?
All right, excellent. Anna. I think you're muted, Ivana.
Thank you, sorry. So great talk, Jandrie. So you think that this globular cluster may have been recently disrupted? So I was wondering if you have considered looking for additional evidence of that in the form of like any streams of stars that might result from this globular cluster along its projected orbital path?
Do you mean, sorry, did you say to find its origin or to find how massive it was?
I mean, for additional evidence that this globular cluster was previously more massive and has been disrupted. Like if you found, you know, some streams or something like that that agree with the globular cluster's orbit, that would provide additional evidence in favor of this explanation.
So I believe that, so I plotted it on a intricity versus radial momentum phase diagram. And we found out that ESO280-SC06 falls in line with stars that were born in the Milky Way, but also that it has some alignment with other stellar streams. So it is a bit unclear exactly like how we would define if it was always orbiting in our galaxy or if it came from other stellar streams. But I believe with working with Anna a bit more, we can find other ways to find evidence that it was previously more massive.
I see, thanks.
Madeline, do you have a question?
Yeah, I know this is kind of part of the like unknowns, but I haven't done really any work with globular clusters. So looking at the trend that you were comparing your globular cluster to, I guess like some have a lot of like of these weird stars that you were talking about. And so is there anything indicating like why more or less would be added to it?
Yeah, so the trend is mostly that the more massive the globular cluster is, the more amount of enriched stars it has. but there is actually no explanation. Like no one really knows why these enriched stars happen. So it's more of like day-to-day of just looking at globular clusters to take a closer look to see why they behave this way and why these like big chemical abundance ranges happen.
Very interesting. Thank you.
You're welcome.
Awesome. I think, Ilva, we have time for your question and then we'll need to move on.
Great, thank you. Hi, Jandrie. Thank you so much for this very nice talk. It's really cool to see your results. I am curious about this barium enriched star. Of course, since you say that it may have been affected by an AGB companion, and I was wondering whether you have any idea of how massive this star is, and whether it was enriched in barium and nitrogen before or after it got enriched in the other elements.
So I actually do not know. I will have to talk to my mentor and get back to you. That is a very interesting question. I would want to know that too. So thank you for bringing that up.
Okay, cool, no problem. So just as a follow-up, do you know roughly how old the globular cluster is?
Around 10 to the 0.5 billion years. 10.5, sorry, billion years.
10.5 billion years. Okay, thank you so much.
You're welcome.
Awesome, wonderful. Let's thank Jandrie again.